lecture, blah, blah, blah. Yeah. Is there any questions about the timeline and these things? At this stage, I forecast that we will finish the crash course probably late October. So possibly early November. Okay, so there is no question, and everyone can still hear me, right? I don't have our friend Soham to... Yeah, okay, good. Okay, so let's crack on. Welcome to part A. So the first thing we need to do is the notion of path, okay? So giving a topological space and 2 points, let's label them P1 and P2. I could have put P0 and P1, but it doesn't matter. Let's call them P1 and P2. We say the 2 points, P1 and P2 are connected by a path if there exists a continuous map from the closed interval 0, 1 to the space X, such that, so the continuous map gamma, such that gamma of 0 equals P1 and gamma of 1 equals P2. That's it. So the only requirements for this to be a path is that it has to be a continuous map. Okay, from this 0, 1 interval, this is understood as a topological space, as inheriting the subspace topology of the standard topology on R. Okay, so we say the 2 points are the P1 and P2 are the endpoints of the path. So P1 is the initial point, P2 is the endpoint. So intuitively, this is essentially just an abstraction of being able to, walk from one point from P1 to P2. Okay, walking it in a continuous manner without interruption. So yeah, here's a picture for you to just have an overview of this. So this is just an abstraction of being able to walk from the space to enable you to walk from any from point P1 to P2. Okay. And there's another thing is if gamma, as I said, gamma in here, the only requirement is that it's continuous. It doesn't necessarily need to be a homeomorphism. But when it's a homeomorphism, then this is called arc path. I've heard this term, or just arc from P1 to P2. Okay, yeah. There is also another notion called loop, and these things in case when gamma of 0 equals gamma of 1, but that doesn't matter. This is something that we will cover later when we talk about homotopy and these things in the next module. Okay. And another thing to note is that obviously if P1 and P2 are connected by a path and P2 is connected by a path to P3, then P1 and P3 are also connected by a path. Okay. In fact, this means this essentially the relationship, the path connectedness between 2 points is actually an equivalence relation. Okay. So you can define this like P1 and P2 are equivalent if and only if the 2 points are connected by a path. So this is an equivalent relation. Now, wouldn't it be nice that we have given a space? Obviously, at this stage, there's nothing that tells us that there is a path between any 2 points. But it would be nice to have, to be able to go from one point to to be able to go from any 2 points, right? So that will be great, right? So this is exactly what leads us to the notion of path-connected space, as you already guessing. So a path-connected space is a topological space that have this property of every 2 points are connected by a path. Okay, so X is a path connected if every 2 points P1, P2 can be connected by some path gamma. Okay, so intuitively, this means that in this case we are able to walk when you pick any 2 points, you are able to walk from between those 2 points. Okay. This from a physicist on the audience. This is great for you guys, right? Right, to be able to walk from any given point. It's great, right? And another thing is if X is called arcwise connected if there exists an arc path between an arc between any 2 points. And something very interesting it does is that if a Hausdorff space is path connected, then it is arcwise connected. In fact, Hausdorff space is path connected if and only if it is arcwise connected. So you're already starting to see, you will see more the interesting properties that Hausdorffness can give you, which is why, in fact, some authors actually, they take path connectedness and arcwise connectedness to be the same, but this is only true when this is when it comes to Hausdorff spaces. Okay. Now, here's a proposition. This proposition shows that I hope you can see this, and that path connectedness is a topological invariant. Okay. So, given two topological spaces, X and Y, if X is path connected and F is a map, a continuous map from X to Y, then the image of X is path connected. So this means that obviously we can use path connectedness to assess whether two topological spaces are homeomorphic. So it's another invariant in our toolbox in order to assess whether two topological spaces are homeomorphic. Okay. Very often this is very useful thing, as you will see in a minute. Much more intuitive in terms of finding out than connectedness. Yeah. Let me see. So we have a question. Let's see if we have a question. What would you? So Amir is asking, what would homeomorphism look like with a path? I will actually leave that as an exercise. Just imagine. Okay. In fact, take some of the examples that in the challenges that I'll come one of the spaces and try to imagine if the path, instead of just being continuous, if it's a homeomorphism, to see what it will give you. This will help you get into how these things work by yourself, because the key is that for you to be able to see this. Okay, so and here's a very important theorem. Unfortunately, I didn't have time to provide a version of the proof, but the textbook will definitely have this. And you can also try to prove it by yourself. It's not that hard to prove, really, this thing. And if you are having some issues understanding the reference materials of these things and you want another version of the proof, I'm happy. Ping me on the thing on the chat. Okay, so as you can see, so if a topological space is path connected, then it is connected. This is very handy. So it means if you can figure out that a space is path connected, intuitively, it's very often for a lot of spaces, especially the ones that you can draw, it's very easy to see that it's path connected, and then it immediately follows that it's connected also. Yeah. So this is actually what a lot of very often is what people do when they want to prove that a space is connected. The first thing they will try to do is to try to see whether it's path connected first. To see if it's path connected, then it immediately follows that space is connected, because path connectedness is a stronger notion, and it's also from an intuitive point of view, especially for those spaces that you can draw, you can have pretty good idea whether a space is path connected or not, just by looking at it. Now, it's very important to know that the opposite is not true. A connected space doesn't necessarily need to be path connected, okay? A good example of this is the so-called topologist sine curve, which is connected, but it's not path connected. You will see, probably, I'm pretty sure you will have this on the thing, on your study book, you will have this. If not, you can just Google. But just to think, just to for your node, it's very important to know that connectedness does not imply path connectedness. Okay. Okay. So, are you guys still with me? Yeah. Okay. Good. Yeah. Okay. So Barry is saying it doesn't have to be. Yes, it's homeomorphism is bijective. Yeah, it has to be bijective. Yeah, that's true. Was there any confusion in terms of the proposition? I guess you're talking about here. Well, I mean, you can see if this is a homeomorphism, then obviously it means that the thing f of x equals the entire space y, right? So it means that f of x, in this case, if this is onto like one-to-one, this is a homeomorphism, then it means like, obviously the entire domain of this is the entire space, and f of x equals they are homeomorphic. So the connectedness, the path connectedness is preserved in this case. So that would mean that y is also path connected. Okay, cool. Okay, so here's a challenge. I really encourage you, even if you struggle to do it yourself, even if you have to look at the study materials and these things, just make sure that you understand exactly why these the spaces, hopefully some of them are, maybe others are not path connected, who knows? This is a challenge for you, but try to do it by yourself. And then if you cannot do it, even if you look at the material, try to understand why, okay? Because it's really important. So the first challenge is that suppose X and Y are path connected. The question is the product also path connected? Yeah, no Googling, huh? No, just try to think it through yourself. And then the second challenge is which of the following spaces are connected and therefore path connected? So, for example, the closed interval 0, 1 equipped with the subspace topology of the standard topology in R. And this one, the open interval 0, 1 equipped with the subspace topology of standard topology. Also, the circle equipped the torus. Some of these are like you can draw them like the old stuff. You pick you blindly pick any 2 points. It will give you the intuition whether they are connected or not. But I still want you to think formally. To essentially try to build a continuous map actually. Try to build a concrete paths between the points in the thing between in the space. Try to build paths in the space, concrete continuous maps. So it's not just you are drawing just relying on your intuition, but do it formally. I encourage you. And then he's saying which of them are connected, which of them that have paths that are homeomorphisms. Okay, so I hope you have a nice challenge here for you. Some of them are tricky, others are not the thing, but but it's very important that you go through this, try to to do it by yourself before you look at any other alternative solution. Okay. Now, so connectedness and path connectedness are very interesting concepts, but there are other concepts that are built on them also, a follow-up concept, let's say. So one of them that we left out, we didn't want to, because this is a crash course, we don't really want to want to go there. But I just wanted to comment 2 of them. So in fact, 3 of them. One is called local connectedness, and another one is local path connectedness. Okay, so connectedness and first of all, connectedness and path connectedness are what topologists call global properties of a space X, and X being topological space, not SpaceX from Elon Musk. So essentially, these global properties say something about the space as a whole, whereas local local properties say something about what happens locally at arbitrarily small neighborhoods of points. So if you zoom in, with a microscope, you go down, these local properties tell you what happens at a local level. So local connectedness and local path connectedness are local properties. They are not global properties, okay? So we didn't touch this, so just to let you know, there are these other concepts also. And the relationship between them is also similar. So locally path connected is also locally connected, okay? Just like the parent global properties, okay? Now, it's very important to know that global properties do not imply local properties and vice versa. For example, a space can be locally path connected, but it fails to be path connected at a global level, okay? So it's very important. This is one of the things that I think you already figured it out. In topology, there are so much pathologies and these things that one has to be very careful, especially when it comes to generalization, okay? Another very important concept that we didn't touch, who knows, maybe we will probably touch this at another course on algebraic topology, simply connected spaces. Yeah, so this is essentially a way of, for example, how can you prove formally that a sphere is not homeomorphic to the torus? Formally, yeah? I mean, intuitively, you can look at this and say, okay, well, there's a hole in here. This one doesn't have on the thing, or in that. And more formally, this has genus 0, this one has the genus 1. But you can't just say that mathematically. You need to formally prove this. This is where this notion of simply connected comes into play. This is essentially, in a nutshell, it's a tool that enables you to detect holes, whether the space there are holes in the space. Okay, but to formalize this notion, we will need the concept of homotopy, which is essentially what the tool that helps you detect holes in space. We will not do that in this crash course. We will get into homotopy in module 2, because I want to talk about the fundamental groups and these things as one of the first few lectures on the thing on module 2. So you will learn about a little bit more about this, what homotopy is, and the fundamental group and these things. And hopefully later, maybe next year, we will have a course on algebraic topology. You will even learn more tools, abstract tools, to help you, compute, topological invariance and these things. You will learn things like homology and these things, okay? But for the time being, just we'll keep it simple. Okay, let me check. I'm always staying because I don't have anybody on the thing, so I have to ask again. Am I still with you? Yeah, okay, so everyone is there. Okay, excellent. Okay, so far, so okay. And here's how these things are nested together, just to help you picture these things. So connectedness, as you can see, obviously path connectedness is connected. The same way also simply connected is path connected, is path connected. Okay, so this is how these concepts are related. So hopefully this gives you a picture on these different notions of connectedness. Okay.